Well, hi there, folks, and welcome back. We're going to get into lesson 2, which is the biochemistry of how nerve cells fire. We're going to look at how that signal can get all the way, for example, from the brain down through the spinal cord, from the peripheral nerves, and make your foot move. How do we get that motor neuron to do what it does? Well, it's a little bit of chemistry. And what are we talking about here? Well, if we go into lesson 2 specifically, you'll notice I put this graphic at the top. The reason for that is I wanted to show you that the inside of the axon, the inside of the cell, tends to be quite negatively charged. And there's some special chemistry here where the outside or the exterior of the cell is quite positively charged. Now, that's not by accident. That's actually done through pumping systems that maintain this charge difference. Now, wait a minute. This is where biology and chemistry and a little bit of physics will come together. Because if you look at a typical battery, you have a positive end called a cathode, and you have a negative end called the anode. And if these are hooked up, what we can do is we can cause an exchange, and you get an electrical flow or an electrical discharge. So the idea of a battery here, I just want you to think of this cathode here and this anode here, because that's exactly what's been set up all along the membrane, the exterior to the membrane, and the interior of the membrane of your nerve cells. Think of them as all little batteries that are ready to discharge. And that's a very good analogy moving forward. And we'll look into the chemistry of this. Down here, you'll see a graph and you'll say, oh my goodness, what the heck is that? Well, what we're going to look at with the cells, we'll look at just how much of a discharge is there and how much of a recharge occurs. Now, a little bit of terminology. Let's make this a little bigger. Depolarizing is like when something fires. Okay, so when the signal goes. Repolarizing is what we call a recovery phase. Now, one thing I want you to know about nerve cells, they either fire or they don't. Down here you'll see maybe you bumped into something, but it wasn't quite enough to cause, a sensation of pain. There's a certain threshold that will cause a nerve cell to depolarize, and it's considered to be minus 70 millivolts. Once that nerve cell fires, it will do so, and then it has to recharge until it can go again. And I've had students look at this and say, that looks a little bit like an EKG. Well, it is in a way, because you were looking at electrical discharge in the heart, but now you're going to be looking at a specialized graph where the resting state of a nerve is around minus 70 millivolts. And once the impulse passes by on a voltage meter, we can detect it at positive 40 or plus 40 millivolts. And then your neuron does get tired. There's a point right here we call the refractory period where there's no way the nerve can fire again until sort of the chemical battery is reset. Okay, quite a bit to get into here. So, fire up my iPad, fell asleep on me. And there we go. So there's three major areas that we have to focus on with the conduction of an electrical signal. First, we have something called the resting potential, and that's the minus 70 millivolts. It has the potential to fire, so think of it as its chemical energy before it does so. Then we have the action potential, which is literally the action phase. There we go. So I'll just change my color here. We'll go with that. The action potential phase, where the chemistry happens, and we'll look at the sort of the electrochemistry there in detail. And then the refractory period, which you can think of as recharging. Once you're recharged, you're resting and you're waiting as a nerve to fire again. So your refractory period is not something you can overcome. You need a chemical reset at that point. So you need to know these three: resting, action, and refractory. And again, I kind of went over it a little bit in advance, but those nerve cells, they follow the all or none concept, right? You reach threshold and the nerve fires, or you don't, and it doesn't. Now, where nerves will fire, for example, if you're feeling pain, you've got little pressure receptors or even pressure receptors, pain sensors, pressure receptors in your fingertips, and they'll only fire if there's enough stimulation. Once they fire, the action potential will start, and as it travels down, when it really gets going is right at the kind of the hill just before the axon. We call that the axonal hillock. Let's take a peek. Let's take a little peek at that. So just a second here. Where was it that I wanted to show you? Ah, zoom up. That's what I wanted to show you. It's interesting that this is the last part here because it's actually the most important. So if you zoom out and you look at the dendrites here, they've received a signal. I'm actually going to just want to reload this again. Went too fast even for me. So if, let's say it's pain or pressure or something like that, and the signal has come down from here, which is the axonal hillock, and it travels down the axon, keep your eye on this. You see this exchange where we've got ions on the inside and the outside, and I'm seeing basically a reverse of polarity here. Well, it's that signal, that reverse of polarity, that will get the signal down to your effector, and in this case, we can raise the foot. Let's look at that one more time. Now this time, as you're watching, observe how the positive charges go to the inside of the membrane, and the outside of the membrane becomes negatively charged. And after it's done, there's a little recharge here. It's amazing how many things are shown in this animation. So we have to look at that in detail. What's up with the exchange of ions? In order to explain this to you, I have to go right down to the membrane of our axon. So what's going on there? What's going on with these discharges here? Well, here's what is occurring. Resting potential. There we go. If you look at the membrane in cross section, okay, if you remember, these are your phospholipids, right? There's little phosphate heads and your little triglyceride tails sticking in there, right? Or sorry, fatty acid tails sticking towards the inside. What happens when the signal comes along is that the outside of the cell is positively charged, so this is exterior, and the cell's interior is negatively charged. There's a lot of protein on the inside of a cell. That's quite negative. You'll find chloride or chlorine ions on the inside, and the cell uses a little bit of energy to make sure that there is this potential difference between the outside and the inside. Outside of the cell, the reason for this is that there's a lot of sodium waiting out there. So what I'm going to identify this as now is a large amount of sodium. And if we let it in, if it rushes in, we can basically depolarize the membrane, and that will cause the little electrical impulse to shoot along the cell membrane. So at resting potential, what you've got, and this shows it here in a little more detail. This one's a little harder to see. In the outside of the membrane, you've got sodium ions, and they have been pumped out here. And on the inside, there's our negatively charged protein, right? And you'll notice, you'll look at this and you'll say, okay, there's chlorine on the inside. Yep, it's not really being represented fully here, but there's a lot more negative things on the inside. Don't let this picture fool you. There's a lot of protein on the inside, and there's also potassium ions. You'll want to keep your eye on these. These are all the actors we're really going to care about. In order to study the action potential, there's two major actors to keep your eyes on. There is sodium and there is potassium. So this is a sodium-potassium sort of dance. So what happens, all the sodium is loaded on the outside, and there's lots of it. There's so much sodium that it's like an army of sodium out there, and it's positively charged compared to the inside of the membrane. So what occurs? Well, at resting potential, your sodium is on the outside, and when depolarization happens, what we get the opening of the sodium channels. And actually, I think the best one to show you, I'm going to go with this. This one's actually a lot better. Pause right there. So what's happened is you notice that the red sodium gates have opened, and they open in response to the signal arriving. So when this impulse arrives, and it's almost like in your dishwasher when the little soap dispenser opens, sort of you hear it clunk automatically. Well, this signal arrives, and those sodium channels just open, clunk. And what happens is, if you pay attention to the membrane potential, it goes from being negative, and all of a sudden, because of this rush of positive charge, we get a firing. So there's our threshold right there, and then depolarization happens, also known as firing. There's so much sodium flowing to the inside. Remember, it's an army of sodium out there. Okay, that the if you detect this with basically for the millivoltage, you'll see on a graph that it will approach positive 40 millivolts as now your potential difference across the membrane. So I'll just hit play here. There we go. Now, what's happened is your sodium has flooded in. As sodium floods in, you get this net positive charge. So now the inside of the membrane is positively charged, and the outside is becoming negative. So this is like a discharge of the chemicals. You have to keep your eye on potassium. This is where some students get a little confused. They'll say, but Mr. Bleecker, potassium is rushing out. Well, what I have to say is not as much sodium is rushed in. Potassium gates open just a moment after the sodium. So you can see here that the sodium gates are closed. As soon as those sodium gates close, the potassium gates will open. Now, there's a much greater influx of sodium than there is potassium. So even though a bit of positive charge goes to the outside, that's not as much as the positive charge that went to the inside. There's an army of sodium in here. Just because potassium leaves, it doesn't mean that the outside is considered net positive. So it's net positive on the inside. So you can think of almost, I remember my professor saying, it's like the potassium runs away. There's too many positive charges on the inside, and potassium gets out of town. So what you've seen here is that sodium runs to the inside of the membrane, and then just a split millisecond later, potassium goes outside of the membrane. Net charge on the inside is positive. Net charge on the outside is negative. It's not nearly as positive on the outside. And if you follow this, as soon as those potassiums started rushing out, what this is doing is you're seeing a dive in the millivoltage. And that's called repolarization. It's almost like this thing's trying to recharge. It's fired and it's repolarizing or sort of recharging. And what you've got now is you've got net positive on the inside, net negative on the outside. Well, that's kind of strange because the impulse, now that it's gone by, what's the next impulse supposed to do? Think about it this way. The actors are all in the wrong spots. In order for the signal to be carried on, sodium has to rush in. So we need to hit reset, almost like rewinding this. We need to get all the actors back to where they started. And this is how it should be at minus 770 millivolts. So again, just watching the action potential. Okay, there you go. Here's the rush with the sodium gates. And there's the counter rush with potassium. And you notice right here, we're hitting what's called a hyperpolarization phase. In other words, think like you're an actor and you've just done the whole play. And somebody says, oh, you have to start again. You would all be in the wrong position. Everybody would have to get back to their original spots just to start this whole thing up again. Right now, if a signal comes and arrives, this membrane, this portion of the membrane is not ready to fire. It can't fire. It's beyond polarized. What we say is it's hyperpolarized. So nerve cells fire or they don't. And in this case, this is not ready to fire. So luckily, what we have is we have some little pumps, and they put everybody back to where they should go. And it's called a sodium potassium pump. And I'll show it to you in a minute. If we didn't have it, our nerve cells couldn't reset, sort of chemically reset, to do our next play. And right there, it's too bad I can't drag that. Right there, at this point, you see everybody go back to where they're supposed to, and you're back up to minus 70 millivolts. And that's where you're supposed to be. That's how you're supposed to be resting in case that an action potential comes by and you want to get in on that. So watch it one more time, start to finish. And this is on the course site. Just give you a moment to reflect on this. There you go. There's the whole play. Now the sodium potassium pump is the very last thing that kicks in, and it gets everybody back to where they need to be. So the sodium potassium pump is right. Just one moment. No, that doesn't show it. There we go. Sodium potassium pump. I just want to show you an animation of it. Is very important. It's the reset button. One moment there. Repolarizing. Here it is. Now what you'll see what happens is to get all the actors back to their original positions, the sodium potassium pump here will take the sodium that is built up, these little green balls here, and it will pump them to the outside. And you could think of it as an enzyme, which is exactly what it is. It's an enzyme that has the ability to take 3 sodiums here and dump them to the outside, and to take 2 potassiums, the purple ones, and dump them to the inside. So let's see that again, just focusing on repolarization right here. So there's the sodiums going out, and there's the potassiums going back to where they should be. Perfect. Now when that happens, the cell membrane can repolarize. So this is going to take a little while, but we'll get all of these positives, many as we can, to the outside. And this is an active process. So this requires something we call ATP. If you zoom out here, now as you watch this, you can visualize, here's your sodium and your net potassium on the inside. And as this is moving along, that's the influx of sodium, the outward flux or exflux, I guess, of potassium. And then afterwards, this little sodium potassium pump got everything back to where it should be. And because of that, the signal makes its way all the way down the axon, and it gets to the end of the axon, which is our next lesson, and causes the effector to do something. It's pretty miraculous, isn't it? I always like to refer to Sarah McLachlan's song lyrics. It's just an ordinary miracle, because that's how the signal gets from your brain all the way to your toes. That's it, ladies and gentlemen. Thanks for listening. That's the end of the action potential.